In this video, we'll look at 3D convex hulls. First, let's look at some basic definitions and concepts. So, given a set of points in 3D, the convex hull of the point set is a convex polytope that may look like something like this. As opposed to 2D convex hulls, 3D convex hulls are slightly more complicated. In particular, they have zero-dimensional objects known as vertices, one-dimensional objects known as edges, and two-dimensional objects known as faces. So for example, that's a vertex, that's an edge, and that's a face. The first thing we'd like to show about 3D convex hull is that their complexity is linear. In 2D this was obvious because in 2D it was simply a polygon and it had n edges in the worst case. The complexity could be slightly larger in 3D, but it's not beyond linear. In particular, what we're going to show is that the surface of the 3D convex hull is pretty much almost equivalent to a planar graph. There is one easy way to see it. If I define the concept of upper hull and lower hull, if you just take the upper hull and project it down, it will be a planar graph. Similarly, if you just take the lower hull and project it down, it will be another planar graph. So you could easily show that the complexity of a 3D convex hull is not much more than just two planar graphs. But we can do slightly better, and we can just show the whole thing with one reduction. I will go over it because the idea is actually very nice and cute. Imagine that this 3D convex hull is made of wires, and all these faces are empty and the space between it is empty. And imagine that I will place a light source at the top of this 3D convex hull. So imagine that I place an infinite surface below this 3D convex hull, somewhere like this, and the topmost point with respect to this surface is defined to be the top of this 3D convex hull. Imagine that this point is now a source of light. What happens here is that any triangle on top of this 3D convex hull will create a shadow. What I would like to prove is that none of these shadows will intersect. So the shadows of two edges will not intersect. This follows simply by just using the convexity of a convex hull. If I go back to the 3D convex hull, the shadow of a triangle is obtained by connecting the light source to a point on the vertex and then extending it until it hits the plane. How is it possible for two of these things to intersect? It is only possible that if this ray intersects the convex object twice. So in other words, this ray of light will intersect one edge of the convex hull, so creating one shadow, and then it will intersect another edge of the convex hull, and so the second shadow, and then that will be the intersection of two shadows. So that's how we could get intersection among the shadows. So in particular, if I have a light source that is completely outside the convex hull, you can easily see that there will be lots of shadows that are intersecting because there were lots of rays that intersect one edge then hit another edge. But if the light source is on a vertex, all the rays of light that come from light source are coming from inside the convex hull. And we know that any line intersects the convex object at most twice. They have once on this and once when they exit. This shows that the shadows that are created by the source of light cannot intersect. So therefore we get a planar graph. So the only complication here is that the vertices, the edges that come and end at this light source will create shadows that go to infinity. So technically it will be an infinite planar graph with some edges going to the infinity.